This video is going to take us through phase changed. Now we're going to talk about in this video temperature, kinetic energy, and potential energy of particles, and graphing of matter. All right, so the first thing we're going to talk about is the kinetic theory of matter. Basically what this is that matter states that all matter, the kinetic theory of matter states that all matter is in constant random motion, no matter what. All right, so you mean to tell me that matter is moving even when it's solid? Yeah. All right, that's what I'm telling you. It's easier just to show you. All right, so depending on when you're watching this video, we may have done this or may not have. All right, but when matter is in a solid state, so this is just neon. This is representing neon atoms. When matter is in a solid state, you can see it's in constant random motion. All right, now these particles, they don't have enough energy to overcome the attraction to each other. So what happens is it creates a definite shape with a definite volume. All right, so think of it like an ice cube. This is neon. It's much colder than an ice cube, but you think it has a definite shape, has a definite volume inside it. Now, if I add a little bit of heat to it, what happens? Well, now these particles, they have enough energy to overcome. They have enough energy to overcome that attraction between themselves, and so now they begin to kind of spread out, and they can kind of move. They can slide in between each other. And what happens then by just adding that little bit of heat is that turns it for them from a solid into a liquid state. All right, so they can slide past each other. It has a definite volume, but it does not have a definite shape because these particles now have enough energy where they can kind of move. They're not enough to break free from each other, but they can kind of slide past each other. Well, if I continue to add heat, what happens? Well, now they get a ton of energy, and they start flying around, moving past each other, bumping into each other. And what happens now is that they have enough energy to break free from each other, and that creates something we call a gas. All right, so now it's measuring how fast they're moving. All right, and this is a really, really low temperature. All right, so that's what's happening to matter on a molecular level when we're talking about temperature. The more you are increasing the temperature, the faster those objects are moving, because that's really what temperature is. All right, so temperature is the average kinetic energy of the particles. Do we already study that? Yeah, we did. Oh no, it's the dreaded formula. Basically, all I'm telling you here is that temperature is basically dependent upon the mass, but more importantly, it depends on the speed, because you're squaring that velocity, so it depends more on the speed of it. All right, so think of a thermometer like a speedometer. The higher that thermometer is, the faster the particles are going in that whatever you're taking the temperature of in that substance. All right, so the faster something is moving, the higher the thermometer is, that means the faster those particles are moving. All right, so temperature, basically the reason why that is, once again, is when heat is added to a substance, that energy, we said energy is not created or destroyed. We're kind of going back to energy here for a second. So when you're adding heat to a substance, that energy is being converted into kinetic energy for the particles. Essentially, they're getting energized, and they move faster and faster, and eventually they move further apart. This is why most matter expands when it's heated, because particles are energized, they move further apart. So like hot air, that's why hot air balloons work, because they're able to float in the air. So that the air inside of the hot air balloon is less dense because it's moving faster and further apart, so it becomes less dense, allowing the balloon to lift up. Whereas colder air is not moving as fast. Most matter shrinks when it's cold, because it's less energized, they're moving slower, and that force causes them to come back together. Water is one of the few substances that is created that actually expands when it's cold. And that's just because of the shape that it is. If I go back to this little simulator real quick, if I click on, and we would probably have already done this if you've done it. But water, when water is a solid, you can see it has all these holes and these gaps because of the structure that the water molecules create. It actually expands from when it's a liquid to when it's a solid. All right, most matter expands as you go down. It will expand as you go down. It'll shrink as it gets colder. But as they move slower. So you can see how it expanded when it went from a liquid. When I started taking heat away, it expands. It kind of blows up, because of the structure it creates. That's pretty rare. That normally does not happen with matter. All right. And so a phase change, basically, eventually that energy becomes so great that we talked about how that the force, they will start to break free. If it's in a solid state, it'll begin to flow past each other because the energy becomes great enough to where they're not stuck in a fixed position. Those molecules are not stuck in a fixed position, so they're able to flow past each other. And this is when it changes. This is beginning the change from a solid to a liquid. So the particles have enough energy now to where they can kind of start to flow past each other, and they change from a solid to a liquid. Now, it doesn't happen all in one time. It happens in a process. During that process, the kinetic energy or the temperature does not change. All right, so when you undergo a phase change, the temperature doesn't change. If heat is being added to a substance, the kinetic energy doesn't change. Where's the energy going? All right, so if I'm heating up something, if I'm heating up an ice cube and that ice cube is melting, but it's staying at 32 degrees, because that's what we're comfortable saying, 32 degrees, how come if I'm continually adding heat, where is it going? Well, it's converting into potential energy, because potential energy is created as the space is created between the particles, they start to move further apart. That's increasing the potential energy. So by adding heat, even though the kinetic energy doesn't always increase, the potential energy will increase between the particles. All right, and a lot of times we will show this by using a heating curve. All right, this is an example of a heating curve. It looks like this. It has several plateaus as something is heated. All right, temperature is on the y-axis, time is on the x-axis. As temperature is increasing, all right, it's showing this process, and you can see these plateau. At the plateau, this means that a phase change is occurring, because we said temperature is kinetic energy. All right, well, if it flatlines here, as heat is added to a substance, you'll see a heating curve, and we'll do this. A heating curve, it'll flatline. Why does it flatline? Because the potential energy is increasing. No longer is the kinetic energy increasing, but the potential energy is increasing. There's more space, and now once it's all turned into a liquid, now you can continue to heat it, and the liquid will begin to heat up. And then once it heats up, it'll turn, the particles will start moving faster and further apart. All right, and so just like this, like on a heating curve, when we look at a heating curve, this is what it'll look like. So at point A, that would just be a solid that is being heated up. All right. At point B, when you see these plateaus on a heating curve, what that means is that it's changing. It's undergoing a phase change. Well, since at the coldest temperature, objects are a solid at their coldest temperature, and then as energy is added to it, as temperature is added to it, it will undergo a phase change. Well, now it's turning from a solid into a liquid. And then as the temperature, once this goes up at point C, now right here, this is called the melting point. All right, so it begins to melt. And then once that entire process is underdone, it takes time. It doesn't happen all at once. It takes time for the whole substance to melt and for the potential energy to increase between the particles. And then once that happens, once again, notice temperature doesn't increase during a phase change. The kinetic energy stays the same. Potential energy increases. And now the kinetic energy is increasing and the potential stays the same. All right, so all we're doing is the liquid is heating up until it gets to this point, which is known as the boiling point. Point D is the boiling point, where the liquid is starting, enough energy has been added to it to where now the liquid is going to start to break free and become a gas. All right, so that is what is happening on a heating curve, and then eventually it becomes, obviously, point E is a gas. So if you look at a temperature, if you look at a heating curve, you'll see these various plateaus, and that's what's happening. Here you just have the kinetic energy is increasing, plateauing, kinetic energy increasing, plateauing. Here, the potential energy staying the same. Here, the potential energy increases. All right, so because there's more space needed between the molecules in order for it to become a liquid, more space created between the liquid when it's becoming a gas. All right, so that's what's happening in this way. As you increase the heat, it's turning from a solid to a liquid, and then as it goes from a solid to a liquid, and a liquid, you can see some of it's still a liquid. Eventually, they're all going to break free and become a gas, and more energy is required. All right, so that's what happens under a phase change.